Hello everyone, this is Bhavik. In this video, I'm going to explain my Geogebra project called root approximations using Geogebra. So there are many methods to calculate or approximate the root given a function. And in this project, I've covered the four main methods. One's the bisection method, regular Falsey method, secant method, and Newton's method. So these four methods are the main methods that are used to approximate the roots. So these are iterative methods. So it's not an explicit formula that's used to find the roots, but it's an algorithm where we iterate to approximate the roots in each iteration. So let me first cover the usage and then the methodology that's used to create such a graph. End user would just type in a function, any function, like you can type in a function like this, and then next they'll have to set the bounds of the interval. This root is not interesting, it's just 0. Let's try to find this root. So I'm setting up a comma b such that the root lies between a comma b, this interval. And then next I'll have to select the method that I want to implement. So let's say I want to first try out bisection method. So I'll set n equal to 1 and then I'll just click on iterate. So here you can see the iteration number, the number of times you have iterated and the approximated root. And f of this number should approach 0 because that's what root means. Let me iterate a few more times and you'll see that we've approached the root. So this is the approximate value of the root. Okay, let me select another method and the process is same. You'll just have to click on this iterate and then it'll iterate that for you. And so these methods have different order of convergence. So you might notice that bisection method is a bit slow compared to regular Falsey method because in fewer number of iterations I'm able to approximate the root better compared to the previous one. So for secant method, if I start doing the iterations, so here it approaches the root even quickly, and this is the root. And in Newton's method, I'll have only one variable. I'll just have to randomly set that and then iterate. Let's try it again. So I'll just have to select a random point, just drag it, and then once I iterate it a few times, it approaches the actual root because f of this is equal to 0. Let's use our original function as before. Okay, so the way bisection method works is you have an interval. It'll first find the midpoint m, and the next step would be to find whether this subinterval or this subinterval contains the root. So here you can see that this one contains, that's why it's shading this in orange. Let me move this a little, and now you can see that this subinterval is shaded in orange. So once I click on iterate, a comma b would then be a comma b, and then this interval would again be split in half, and this part of the subinterval contains the root. Now again this process repeats. It's again cut in half, and this first subinterval contains the root. So this m will become b once I iterate. So this process goes on and we approach the root. So that's the bisection method. The regular falsy method is similar. Here instead of the midpoint, what we do is it looks like the midpoint but it's not. Okay. So let's say this is my interval a comma b. So for secant method, I'll draw a secant from this point a comma f of a to b comma f of b. In my graph, I have defined it as c comma d. So it's c comma f of c and d comma f of d. I'll draw a secant and then I'll intersect that with the x-axis, which I'm calling it m2. So in the bisection method, I'm just splitting it in half and then choosing one of the subintervals. In the regular falsy method, I'll choose the intersection between the secant and the x-axis, and I'll choose one of these two intervals. Because this interval contains the root, I'm shading that in orange. Okay, see this is m2 and this part contains the root. And if you see here, this is the secant, and out of these two subintervals, this subinterval contains the root, and therefore it's shading that in orange. Okay, now let's iterate. The same process is being used. Each time when I iterate, one of the subintervals will be chosen. But if you notice with the regular falsy method, uh, this endpoint doesn't vary as much. Let's try to do it again. Let's say this is my initial configuration and I start iterating. So this endpoint doesn't change. Let's try to approximate this root. Now b changed, b and see a remained constant. So based on whether the region of the graph is concave up or concave down, sometimes the endpoint doesn't change, it stays constant. With the bisection method, sometimes a will become the midpoint and sometimes b will become the midpoint. Let's try it again. So this is my comma b. See here b is constant. Okay, so that's the regular falsy method. With secant method, we still do find the secant. It's the same secant as before, but unlike the regular falsy method, here we don't choose an interval. We directly update b to be a. I mean a will become b and b will become m3. This intersection point between x-axis and the secant. So here we don't have to choose any subinterval. If you see, this will become a and this will become b, and this process goes on. Now this part will become a and m3 will become b. Now a will be this and b will be m3. And the convergence of this method is faster than the previous two methods. Let's try to view this again. So a would be updated to b and b would become m3. And so in this method, it doesn't have to be the case that a is less than b, because sometimes they flip. Here a is less than b, and once I iterate, a became greater than b. And here a is less than b, but m3 is greater than both a and b. So here it doesn't have m3 doesn't have to be between a and b, and a doesn't have to be less than b. So this is the secant method. The last method is the Newton's method. Here we have only one variable. So what we do is, in the secant method we have two endpoints and we are calculating the secant. But here it's the same version as secant method, but it's like A is getting approached to B. And once A approaches B, the slope of the secant would be approximately equal to the tangent. So here we draw a tangent from this B. We find the intersection with the x-axis. Let's call that M4. And now in the next iteration, B will become M4. Okay, now let's repeat the process. Now this line is drawn and then the tangent line is found, and M4 is the intersection with the x-axis. Now M4, B will become this point M4. As you can see, it's approaching the root. Now we do the same process again, draw the tangent. We have M4, let's iterate. And if you see, this method converges faster than all the previous methods. Now let me show you how I made this graph. These two might look like buttons, but they are just text. And the points A comma B, the x coordinate have defined it under C and D. So if you go to the settings, once I click on iterate, go to this scripting tab. So here I can define JavaScript, which will run this code whenever I click this button. So what I'm doing is, I want to iterate these variables. So whenever I click, I want these variables to update. Observe over here, C and D, they change every time I click on iterate. So the way this JavaScript works is, if you go to the web version, let's say I have a variable. So to get this value using JavaScript, I can do ggb applet dot get value of A. So using this, I can fetch the value of this variable, and then I can use that. And I can similarly set the value also. Set value. Let's say I want to set the value of A to 10. So by running this, it will automatically set this value to 10. So here I've first defined the functions getVal and setVal. And if you see, whenever I'm iterating, I'm updating C to the value defined at C next. So I'm getting the value from C next. I'm defining that in this variable C. And then I'm setting the value of C to C next. Similarly, I'm getting the value of D next, and then setting the value of D to D next. So whenever I click this button, C will take the value that's in C next, and D will take the value that's in D next. So let's say I have a list defined by this. So there's no direct function where you can get these values as an array. So the way I've done is by using get value string. So here I get a string, so, and then I've taken the substring of that. Okay, so I get this part, and then if you do split, you'll get it as an array. So that's what this get list function is doing. It's getting the value as a string and then splitting using the commas and then returning the array. These two functions we are going to use later. So for now, whenever I click on iterate, C gets updated to C next and D gets updated to D next. But C next and D next are not the same because in the bisection method it's different how I'll iterate compared to the regular false C and secant and Newton methods. So if you see, I'm using an if condition saying if n is equal to 1, update that to bisection method. If n is equal to 2, update that to the regular falsy variable. If n is equal to 3, update that to the secant method. Similarly, for d next, I'm again using a condition. So it will set the value of d to d bisection if n is 1. It will set it to d falsy if n is 2. It will set it to d secant when n is 3. And it will set it to m4 when n is 4. And the derivations for these are mentioned in the report. So with the bisection method, first we check which subinterval it lies in. So that part is done over here. So this is C, this is D, and this is M. So if f of t times f of m is less than 0, that means that the root is within here. And so C will become M, otherwise C will remain the same. Similarly, if the root lies here, that means f of C times f of m is less than 0, then D would become M, otherwise D would stay the same. And therefore, when I click on iterate, the values of C comma D change because of the way I've defined C bisection and D bisection. And C next and D next become C bisection and D bisection because n is equal to 1. Similarly, if you go to the regular falsy method, so here I'm calculating what the next value of C and D should be in the regular falsy method, and this derivation for this formula is given in the report. So just like the bisection method, here also I'm checking which subinterval contains the root. So if the root lies between D and M2, then C will become M2. Otherwise, C will stay the same. And if the root lies between C and M2, then D will become M2, and otherwise D will stay the same. So that's what these two mean. So if you see the secant method, those are defined over here. And here I didn't need any other if conditions because here I don't need to check if a subinterval contains a root. I can directly update C to the D endpoint and the value of D to M3. That's what is done here. And M3 and M2 are same because in both the methods I'm using the secant. So only this is needed for the secant method. And for the Newton's method, the derivation for M4 is also given in the report. This is M4. And if you see there's only an extra additional thing I needed, I'll just update D to M4. If n is 4, I'm updating the value of D to M4. So I'll be defining D next to be M4. And this JavaScript will set the D to the value of D next. So whenever I iterate, the endpoint will take the value of M4. So that's how these four methods are implemented. Now for the last part, to analyze how these different methods help us converge to the root and how fast they converge to the root, we can analyze this value. So if I click on iterate, you'll see that this value approaches 0. But if I take another method and start iterating, it approaches 0 with a different speed. And with the secant method, If you see, the rate at which it becomes 0 is different for different methods. Here, in only 3-4 iterations, it became very close to 0. Having a threshold and recording the number of iterations required to cross the threshold. I'm defining d equal to f of this approximate root, and then I'm checking when d is less than 10 to the power of 0, 10 to the power of minus 1, 10 to the power of minus 2, etc. So let's say for bisection method, I iterate a few times. So I get this array 1, 5, 8. What does this mean? It means that after the first iteration, the value of d was less than 10 to the power of 0. After the fifth iteration, it was less than 10 to the power of minus 1, which was zero point 0.1. And after the eighth iteration, it was less than 10 to the power of minus 2, which is 0.001. If you see, if I iterate a few more times. So this was also implemented using JavaScript. If you look through the code, I'm calculating this accuracy value. It's the exponent, where here it's minus 3. That means 10 to the power of minus 3 is greater than this. So you can calculate that using the logarithm. And what I'm doing is I'm checking that whenever it changes, I'll update the value of this variable called accuracy, and using the getList and setList functions, I am updating this array. So whenever accuracy changes, it will add the value of capital N to this list. Let's try to see that again. Now this array is empty. If you see, accuracy is 0, and because the accuracy changed to minus 1, that means that this value became less than 10 to the power of minus 1. It added this value 5 to the end of the list, which means that after the fifth iteration, this value would be less than 10 to the power of minus 1. Similarly, if I do the next iteration, it became minus 2 once I reach the eighth iteration. So this would help keep track of the rate of convergence of different methods. In the case of Newton's method, only after the first iteration, the error value is less than 10 to the power of minus 2, and therefore it added this one in this position, third position. And after the second iteration, it's less than 10 to the power of minus 5, and therefore it added 2 in the sixth position, and so on. The regular falsy, after the third iteration, it's less than 10 to the power of minus 1. After fourth iteration, it's less than 10 to the power of minus 2, 10 to the power of minus 3. And after the seventh iteration, it's less than 10 to the power of minus 4. So okay, by this we can conclude that Newton's method has faster rate of convergence compared to the other methods. And by using this interactive tool, you can understand how this method works. You can zoom into the graph, click on iterate, and then see how the variables change.